two major activities of inferential statistics are: 1. To use sample data to estimate values of population parameters. 2. To test hypotheses or claims made about population parameters. In this section, we will focus on how to construct a confidence interval to estimate the true value of a population proportion. Here is a recap of what proportions are. And here is what describes a point estimate. We want to have a confidence interval so we can have an idea of how good our point estimate is. When we have an example like 95% confidence of a proportion, this means we can say we are 95% confident that the true proportion lies between two values, as seen in this example above. In the example below, we see a graphical example of 20 different samples and their confidence intervals. Notice only one does not have the actual population proportion in it. Under certain conditions, the sampling distribution of sample proportions can be approximated by a normal distribution. Let's do an example finding critical values for confidence intervals. Example A gives a critical value of right tail area of 0.05, which means its corresponding z-score will also have a tail area of 0.05. So we are looking at a 90% confidence interval. Finding the z-scores, we use our inverse norm function on our calculator. Since the z-scores relate to each other being opposites, once we find one, we also get the other. Example B, we're given a critical value with 0.10 as its tail area, so our confidence interval will be 80%. Again, using the inverse norm function to get the z-scores, we get plus or minus 1.28. Example C, we have the critical value with 0.08 tail area, so we are looking at an 84% confidence interval. Using our calculator to get the z-scores, we get plus or minus 1.405. To create a confidence interval, we need to know what to add and subtract to our point estimate. An example. Writing the error formula down, we see we need the critical value n, p hat, and q hat. Figuring out the critical value, we need to find 1 minus 0.95. We get 0.05. Now we divide that by 2, so now we know we want a z-score with 0.025 tail area. Using our calculator and the inverse norm function on our calculator, we get 1.96 as the critical value. To find p hat, we figure out what 350 out of 1,000 is. Q hat is just the complement of p hat, so 1 minus 0.350. Now we just need to plug in our information and enter it into our calculator. Rounding, we get 0.03 as our error. Next example, we do the same process. Find alpha, which is 1 minus 0.99. So our critical value have a tail area of what 0.10 divided by 2 is. Then use the calculator to evaluate it. We get 2.575 as the z-score. Finding p hat, we figure out what 220 out of 500 is. Then q hat is the complement, 1 minus 0.44. Then plugging all that information into the calculator. We get about 0.057, rounding to 3 decimal places. Now we have all the tools needed to construct a confidence interval. Basically, we need our point estimate along with the error, and we add and subtract it to get the upper and lower bounds. Revisiting the previous example, now we want to construct the confidence interval. Since we did the work already, all we need to do is add and subtract the error we found to the point estimate. So this means that we are 95% confident that the actual proportion is between 0.32 and 0.38. Example B, we do the same process. Add and subtract the error to our point estimate. So we get a 95% confidence that the true proportion lies between 0.383 and 0.497.